Section 6.53, Homogeneous Equations and Euler's Theorem. We are going to do a problem that's essentially proving the converse of Euler's theorem under certain suitable conditions. And so let's look at, suppose f(xy) is a differentiable function on an open domain, and then x, the result of Euler's theorem right here stands. X partial f partial x plus y partial f partial y equals to n f(xy). And you notice I drew 3 lines here just to remind you that these two equations are identical in that open domain, and that will be important. But normally we'll just say equal. Now, what we're trying to show is the premise of Euler's equation, that is f(tx)ty equal to t to the power n times f(xy). Now, the proof goes like this. The proof, we're going to use a trick. That is, we will define f of t equal to f tx ty. Now, at this point, you notice there's so many variables here. How come there's only one here? That's because we consider x, y fixed. That is, it is a constant. Okay, x, y doesn't move. They're not the variables. Only t is moving in this point, and that's why in the problem it is also understood that the tx ty has to be well defined, and that's in a certain range of where we're going to work with t, that it has to make sense on an open interval. So especially including the point where t equals 1, which we will need in a second. So then we have defined f of t equal to this thing, and from there we're going to calculate what f prime is. So f prime of t is equal to, by definition, we're going to take the partial derivatives of this thing, is equal to, with respect to t, by the way, so then it equals to x f1 tx ty. Being that this is a composite function, it's a good idea to write it down so that you remind yourself you're still working with a composite function. This is the rule of differentiation. You have to keep everything inside and then take the derivative of the inside with respect to t in this case. So then we have x left for the first term. And then similarly, for the second term, we have y f1 tx ty. This is f2, of course. Okay, so that's f prime, and then the next thing is we're going to look at this equation, and notice that I put one more line here to mean that that's a completely equal, that is equal every point of x, y. So we will substitute x with tx and y with ty, and that equation will still stand. Substituting, we get tx, copying this thing right here, f1 tx ty. Okay, remember we have substituted this thing, and then with tx ty plus ty f2 stands for that, tx ty is equal to n times f tx ty. Okay, so this thing comes directly from that one, and but notice that this is very similar to this line right here. It's similar to this except for that t. So we are going to put the t in there. So f prime of t is equal to 1 over t times, so we'll multiply and then divide so that the equation holds. So tx, copy that whole thing down, we'll multiply t into this phrase, so we get tx f1 tx ty, and then plus ty f2 tx ty. All right, so that's f prime of t. And now we worked on this, so this is exactly the same as this thing. So we can plug this thing in, which is n over t f tx ty. So we're doing pretty good. We've shrunken everything down to this part. And next, going by the definition of what tx ty is, from here, tx ty is just ft. divided by t, and this is f prime of t. So now we have landed with a differential equation. Now, until now, we have been doing the few differential equations we've done as under the premise that we are given that the derivative is equal to a given function. This is not a given function because we still don't know what f is. However, from elementary calculus differential equations, we have learned before what this thing has to be. If you work at it, you realize what kind of function whose derivative is n times that thing divided by 1t. Well, that is clearly t to the power n, okay? That derivative will fix that. But there's also a constant requirement, and the constant is, here's the constant. The constant is based on xy. Remember, xy is a fixed constant for as far as f is concerned, because we're talking about variation of t only, considering one point of xy at a time. So then we have this, which means that, so the next thing we're going to do is claiming that, so f prime of t, excuse me. So this, I should write this down clearly. So f of t after solving the differential equation is t to the power n times some constant. Therefore, and then f of t, of course, is this thing. So what we have here is substituting this thing back, we get ftx ty divided by t to the power n is equal to a certain constant. That depends on x and y. Now, that means this doesn't change. C does not change with respect to t. That is, no matter what, this ratio is the same. So, this is, I should write it down, this is a constant for t, okay? That is, t doesn't change its value. In other words, let's set t equal to 1. What is that? What happens then? Then we have this whole thing is equal to f of x, y. Since this value doesn't change, and if you set t equal to y, it's still the same value. So then this thing has to be equal to fxy when you set t equal to 1. And that actually is what we're trying to prove this entire time. So that concludes the proof.